In this video, I'm building a planetary gearbox. My goal was to design a robust and powerful gearbox with a stable output. I'll walk you through all the steps to build either a single stage or a two-stage planetary gearbox. To begin, you need a ring gear. It's the part that holds all the components together. A single-stage planetary gearbox is very compact, but it offers significantly less gear reduction. The ring gear for a two-stage version is much wider, but it also provides a much higher reduction ratio since the two stages multiply. In this video, I'm building a two-stage planetary gearbox. The process isn't much different from building a single-stage gearbox. There are just a few extra steps involved. First, I prepare the ring gear with inserted nuts. These nuts have integrated threads, making it easy to screw the various 3D printed parts together. Using a soldering iron, they can be melted into the designated holes. If done correctly, the inserted nuts should sit flush with the surface of the ring gear. Next, I prepare the carrier for the planet gears. Here too, inserted nuts are melted into the back side. Once 3 nuts per holder are installed, the first ball bearings can be added. I'm using standard ball bearings that you can find at any local hardware store. Each designated spot holds 2 ball bearings. The planet gears can now be placed onto the bearings, ensuring a snug fit. They rotate smoothly, which is a good indicator of low friction in the final gearbox. To assemble the first stage, I prepare the output of the carrier. A ball bearing is also integrated into the backside. This will later prevent contact between the sun gear and the first and second stages. As you can see, the sun gear has special recesses that press only against the ball bearing, allowing the second stage to rotate freely without interference. To connect the first stage, I use 3 countersunk screws to fasten the output of the carrier to the inserted nuts on the underside. Here's the completed first stage of the gearbox. The screws are slightly recessed into the top and have enough clearance underneath so they don't stick out. The second stage is assembled in the same way. 6 more ball bearings are installed, followed by placing the 3 planet gears onto them. Another ball bearing is integrated into the output of the second carrier. All parts of the second carrier are then joined using 3 more countersunk screws. Now you can see both stages fully assembled. They're ready to be fitted together, and as you can see, they rotate smoothly thanks to the integrated bearings. For a single-stage gearbox, you could now insert the assembled stage into the ring gear like this. But I'm continuing with the two-stage version. First, I place a large ball bearing at the bottom. This is where the gearbox output will later be positioned and held securely. The gearbox output has special recesses that press against this bearing to maintain the correct spacing between the plastic parts. Here's what it looks like with the output installed. The input stage, the first stage, can now be placed into the gearbox, where it will engage with the second stage. For testing, you can already insert one of the sun gears into its designated position. It also fits into a bearing in the first stage, again minimizing friction between the components. Depending on the gear configuration and ratio, the planet gears rotate significantly slower than the sun gear. To complete the assembly, I once again add inserted nuts to the output. Next, I prepare the gearbox cover. As you can see, there are several mounting points for attaching the cover and additional parts like the motor bracket. First, I insert another ball bearing into the cover. This one will later hold the sun gear in place. You can see that the sun gear fits perfectly into the bearing and has recesses that press against the metal to keep it precisely aligned. Next, I attach the sun gear to a NEMA 17 motor. The sun gear has a hole for an inserted nut, which I melt in again using a soldering iron, pressing firmly until it sits flush with the motor shaft. Using M3 bolts, the connection is secured by tightening a screw through the inserted nut onto the motor shaft. The installation is the same, whether you're using a NEMA 17 or a NEMA 23 motor. I quickly add more inserted nuts into the gearbox cover. Now, all parts are ready for final assembly. The only point where plastic parts rub directly against each other is between the ring gear and the planet gears. That's why I apply a bit of grease here to reduce friction and make the gearbox quieter. The cover is fastened to the ring gear using M3 bolts. To connect a motor to the gearbox, I first screw the motor mount onto the NEMA 17 motor. Depending on the motor type, the mount is either attached to the gearbox first or, like here, directly to the motor. Then, the motor mount is screwed onto the gearbox cover. To firmly connect the motor to the sun gear, I screw in another bolt through the already installed inserted nut. This locks the motor shaft to the sun gear. Next, I connect the motor to one of my encoders for testing. I'm running a basic script that controls the motor, starting slow, then speeding up. I also do a quick torque test by trying to stop the rotation with my hand. Considering it's just a NEMA 17 motor, it takes quite a bit of force to stop it. In my next video, I'll test the gearbox more thoroughly and cover some additional details. Subscribe to the channel if you don't want to miss it. Thanks for watching.